Excel spreadsheet. So I took a couple of measurements across the dish to try and see what it's like. And I guess the main thing you can see on this side here is significantly lower. What I did is I put a piece of string underneath it, leveled it up with just with a spirit level, and then started taking measurements down from the dish. So you can see it's off center. This side here is significantly,
Can
well,
you
several
zoom in?
hundred millimeters
Can you zoom in a little
higher
bit?
than this side over here. Sorry?
Can you zoom in a little bit?
So, what was that?
Can you zoom in a little bit or
I'll
enlarge the
zoom in a
picture?
little bit. Yeah, sure. I think I can. I don't know. How do you zoom in Excel? That's something else
Bottom,
that I
bottom,
have, of course,
bottom
this.
right. There's a scroll bar.
Oh, okay. So, yeah, this is also something that I
There you
have
go.
obviously yet to work out my Excel as well. It's been a long time since I've used Excel, and now I can't actually. Here we go. Get down to the bottom corner again. Anyway, it's a little bit bigger. I just hope I can get away from it. So yeah, so it's got a few bumps. Excel's put in a line here where it should be. So it's certainly not perfect. So Rob and I have been looking at it over the last couple of years, trying to work out what we're going to do with it. So I think we need to put a little bit of effort into that. It wasn't out by as much as I thought actually, but the problem is it's the dish itself is made with chicken wire, and so the chicken wire over the years has deteriorated, so it's got lumps and bumps and holes in it. But anyway, it is definitely there. It's 18 feet wide. So yeah, I probably don't have much more to talk about than that. Really, I still haven't got my radio Jove back together from when I took it away last week. I did get an email a couple of days ago to say that my Super SIDS is on the way. So hopefully, as summer progresses a little bit here, I'll have a little bit more to put in on it. So that's about it, really.
Nice.
I just need to work out how to stop sharing it. Yeah, that worked. So yeah, let me think. Yeah, that's about it, really. Just I'm a bit busy. I'm in the middle of house building at the moment, so I've had concrete pours happening and all that sort of stuff. It's just been hectic. Just went down to Sydney for a couple of days. Went saw Wicked. Any of you guys ever seen Wicked? It's a good show. Good
Yeah.
show. See it if you can.
All right. Anybody got
Okay,
any
that's about
questions
it for
for
me.
Roger?
Thanks.
Oh, I'm sorry. Go ahead. Any more questions for Roger? No, let's go. Steve.
Yeah, good morning, fellas. Just before I start, I'll send some files onto the chat. So while I'm talking, they'll
By the
be
way, there's more than
uploading.
fellows on the line, so just want to make sure you know that.
Sorry, that?
There's more than
More than
fellows.
fellas. Oh, okay. My apologies. Good morning, all. Yeah, so on the chat to everybody is a copy of 2 PDF files. So let's see. I did some work recently on neutral hydrogen equipment. So I'll briefly cover some of these reports that I've been issuing. Where's the first one? This one here, low noise amplifier. Now you guys have probably done all of this, and it's something in your back pocket. You don't have to really think about it anymore. But I've done this for the first time recently, which was to measure the noise figure of a low noise amplifier. One of the last projects I wanted to do before we put our neutral hydrogen receiver back together up on our 8.5 metre dish up at our country property at Heathcote was to fully qualify the low noise amplifier and determine accurately its gain plus a noise figure, something I'd never managed to measure before. This is the radio astronomy supplies item. A lot of you might be familiar with this. I've modified it slightly, as I might have mentioned in the past, by putting a gasket in there, a different top lid, and an air vent, one of these Gore vents, to help waterproof this thing in the weather. There was signs of water deterioration in the previous assembly of that, so hopefully this vent will stop that in the future. Certainly experience has shown that it does. So this wonderful device has a terrific noise figure of 0.29 dB, so it'd be nice to see if it was possible to measure that. And my report is detailing how the process was done, and I can't claim authorship of the methodology. I found it on a YouTube video clip from quite a expert microwave engineer who does this sort of thing in his own laboratory, and he has a 20-minute clip where he explains how it's done. So when I talk about the low noise amplifier, it's not going to be measured on its own. Remember, there's that switch that we decided to put in front of it so we could switch the noise source in and out. So really, we're going to be measuring the noise figure of the low noise amplifier and the impact of this additional loss that we put in front of the low noise amplifier. So this is the physical hardware that I'm going to be measuring. So the original radio astronomy supplies LNA is there, and then it's coupled through to this relay, RF relay, very low loss relay, 0.2 dB loss in that relay. So all of these connectors, the relay and the LNA is what we're going to be measuring the noise figure of. And the methodology is based on gain method. Gain, measurement of the gain of the amplifier accurately, and then measurement of the noise output power of the amplifier. And it's based on a formula. And I give a little bit of a background in the mathematics. In the video clip provided by this Stephen, what's his name? It's the end of the report. I give his name, Stephen Remillard. He's an American, so he provides a lot more detail in the mathematics, going back to some first principle equations. But it ends up just being this logarithm at the end, that formula number 3, where you've just got to measure the noise power in dBm, the gain of the amplifier in dB, and then this fixed constant, which is the room temperature of a 50 ohm load that you use as a substitute at the input of the amplifier when you're measuring the noise power. So I won't go into too much detail. It'll take a while to do it, but you basically use a spectrum analyzer. You need a fairly good one, and I possess one. It's in my own home laboratory, the Hewlett-Packard machine there. And you need to set it up with 1 dB per division vertical scale. You need to use video averaging because when you start out, the noise measurement's very broad over several dB. So there's a very large error band in the measurement. So you want to minimize that down. So you do video averaging, and each sweep of the averaging can take 48 seconds because you're using a very narrow resolution bandwidth as well. And fortunately, my spectrum analyzer, and a lot of them have this, is when you switch on a marker to measure the spot. In fact, in the photograph I've taken, the marker is not visible in there, but it's a little highlighted dot, as you know, somewhere on the trace. You can switch the marker into a mode called noise, on or off. And when you do that, the actual marker measurement becomes a power measurement in dBm per hertz. So you just read that number straight off the screen, and that's what gets put into the formula. And the result I got from the measurement, minus 136.3 dBm. The gain I measured separately with a fairly accurate substitution method, again using a good quality signal generator and the same spectrum analyzer. I got very good gain, and that's almost exactly as specified for that amplifier, 37 dB. And you get 0.53 dB. Now that's a good figure. I'm quite happy with that figure. If you remove that 0.2 dB loss that I mentioned is in that relay in front of the LNA, then you end up with about 0.33 dB of noise figure just for the LNA on its own, which is very comparable to the stated figure by radio astronomy supplies of 0.29. There's obviously going to be a significant error band in this measurement. I have to admit that, and it could be as high as 0.2 dB. So we're in the right ballpark. This is the main thing I was concerned about. And I think this is still quite an acceptable receiver to use, and we'll get good results with our neutral hydrogen studies, in spite of the fact we've added this little bit of extra loss in front of the low noise amplifier by putting in this relay. But the relay gives us this incredible feature where we can calibrate every survey we do. We can use this noise reference. I've measured that in the past. I think I've commented on the fact that this appears to be temperature independent. The output power of that noise reference source is very, very stable with temperature. So we can constantly calibrate our receiver and get really, really good quality scientific measurements. So that's all I'll say on that particular one. So you can read the report at your leisure. And I found it a wonderful way to measure noise figure. Believe it or not, I've never done it before, and I found it very rewarding to get that result. The other thing that we did recently at our Astronomy Society in Victoria was to have a star party last weekend. And it was a very successful event all round. It was mainly for optical astronomy, but we also had a radio astronomy demonstration and loads of new members in our club now. Every star party that we have, which is every few months really, we seem to have another wave of new members join, new people interested in radio astronomy. So there's always something to explain our story to a new bunch of visitors, and they're often very interested. And some of them get so interested they join our particular group and start working on some of our projects, which is terrific. It's good to have that team of people dedicated to radio astronomy start to expand. So we tried to set up a demonstration of neutral hydrogen reception using a small horn antenna that we've got, because our dish, 8.5 meter dish, is still in a bit of mechanical repair. You may know that we wore out that worm drive. So that still hasn't been reassembled. So we had a little horn antenna, and that uses this other radio astronomy supplies device called a 1420 megahertz continuum frequency converter. So you might be familiar with this product. We purchased that years ago along with our other neutral hydrogen receiver. I'd never worked with this particular box before. I had done some work with the low noise amplifier, which is shown there on the right. That was part of that package. This device converts the neutral hydrogen frequency down to 10 megahertz. And it didn't work. Our demonstration on the star party didn't work. It failed. It let us down. So I thought, well, I better take it home and do some servicing and find out what went wrong. And so I started to experiment with this and measure a few things. And obviously it's got a front end board and another little circuit board. No documentation was provided with this, no circuit diagrams or technical descriptions. So I decided to sort of reverse engineer it. And because there's a nice cable there, I could connect an adapter to it and measure each of these modules on their own, which I did. And also noted this, that the output was labeled at 10.7 megahertz, which we were trying to use in our demonstration, of course. And so I started measuring things to see what could be possibly wrong with this whole assembly. I've got a good quality signal generator and that same spectrum analyzer you saw earlier. So I set it up to do this gain measurement to see if there was a loss of performance of this sensitivity of this receiver. And my conclusion was the overall gain, 1420 megahertz down to 10.7, was only 36 dB. And that's well below what the specification is as printed on the box, which is 55 dB. So there's the first clue that there was something faulty. The front end section, however, just this module on the right-hand side on its own, which delivers an output of 70 megahertz, that gain of that amplifier was 59 dB, which is quite acceptable. I also determined that the output of the overall assembly was not 10.7 megahertz. It's actually, with an accurate frequency going in, you were getting 10.017. So I'm not sure why the product was labeled as a 10.7 megahertz output. It's obviously a 6 megahertz bandwidth, but it doesn't really deliver 10.7 out. It delivers 10.0 with a bit of an error on that. And that's not really relevant if you're using a wideband software-defined radio to look at that signal. But if you wanted to do Doppler shift measurements, I think it's a misleading label, to be honest. I have to admit that. What else can I say? So I concluded that with that fairly high level of signal coming out of the first stage, the 70 megahertz converter, it must be something faulty with this 70 to 10 megahertz converter. And so I pulled the board apart and had a look on the other side, the component side, and I found it was quite a sophisticated looking design. I looked up these block items and found out what they were. The two larger ones are mini circuit filters, low pass filters, and this smaller one is a MACOM product, a wideband mixer. So I did a bit of reverse engineering of the circuit diagram, and I drew just the signal path on its own. Obviously, there's going to be an oscillator in there, local oscillator for this mixer to convert down to 10 megahertz. I drew the circuit diagram out of this particular circuit, but I didn't have all the component values. So it just looks like an oscillator. The other thing that you can find if you turn the board over the other way, in the other photograph, you can see that here. So there is actually a quartz crystal sitting on the top side of the board, and it's stamped with the frequency 60.0 megahertz. So it's not a 10.7 megahertz down converter, it's a 10 megahertz down converter. All right, so let me find out. As I've worked with this particular item, I set it up looking at it as an item on its own, 70 megahertz going in, 10 megahertz coming out. And I started poking around physically, scratching it with a plastic adjusting tool on the components to see if there was any intermittence. And sure enough, I started to see a point where the output of the signal on the spectrum analyzer was going up and down by about 10 dB. And this area of the circuit board was very sensitive around that output socket. So what does it tell me? I realized, okay, I've seen this before. I've seen this before, fellas or folks, boys and girls. And I've seen it in a similar construction where a coupling capacitor connected very close to a circuit board mounted SMA connector, the capacitor fails. So I guess that's the message I'm trying to send today, that that's not necessarily a good strategy. There could be temperature coefficient differences in there. This particular socket goes onto an aluminium chassis, and there's a nut that locks that circuit board to the chassis. There could be differential stresses on that connection that translate back to a stress on the capacitor, breaks it, snaps it, goes open circuit. So there's some sort of residual coupling that still makes the thing work, but typically 20 dB down in gain. So I replaced it with a discrete capacitor with wires, and that can have some level of flexibility then, and you won't necessarily have it fail. The other way to get rid of that problem is to have a cable connecting to the chassis connector rather than put mechanical stress on the circuit board itself. All right, so the other thing I determined was that this converter, 70 megahertz down to 10 megahertz, is actually a conversion loss. So you do get loss in that configuration. There's a deliberate 3 dB pad in there. The loss of the low pass filter is not too bad, about half a dB, but the mixer has a conversion loss of at least 6 dB. So that's mathematically it should have been no more than about 9.5 dB loss. But in fact, when it was faulty, it was 22 dB. But when I replaced that capacitor, I got it down to 12.5 dB loss. So that's still loss. That's still RF we're throwing away. So I've made a recommendation to the team that when we use this particular unit as a demonstration, we actually remove that converter, and we convert directly from, I'll talk about this low noise amplifier in a sec. We convert directly from the 1420 megahertz neutral hydrogen down to 70 megahertz, and we then use that because it's quite a good gain. We don't throw away signal, and we can still do research work and demonstrations at the 70 megahertz level. There's no problem with that. So I've ordered a chassis connector that will give us an N-type connection, and it can then go directly to the 70 megahertz output of the that front end module, because that front end module has a cable. So instead of connecting into the down converter, we'll just have another socket here, and we'll have a 70 megahertz output, and that'll be quite acceptable for our purposes. So the other part of this package was this low noise amplifier, and very similar to the one that I reported on earlier, just before. So that was another module that was worth measuring in the same manner, its gain and its noise figure. So that's what I did as the other exercise in this report. This time I didn't do 100 sweeps, I did 70 sweeps, a couple of slight differences in the settings, but the end result was still comparable to what we were expecting. The noise power that I measured was minus 141.4 dBm. The gain of the amplifier, 32.17. That fixed constant again based on room temperature. So I measured 0.43 dB, and the actual specification stamped on that module that we purchased was 0.34. So we're in the right ballpark. It's a very good low noise amplifier. Very pleased with that result. And that'll certainly be quite suitable for our use at star parties and other experiments we might want to try. Because we do have this horn, we can rotate it around. It's a wide beam width, of course, and I still think it'll deliver some useful results for us. All right, that's enough from me. Rich, thank you.
Well, thanks. Now, that's a Spectracyber you just disassembled, right?
Yes, that's correct. Yes.
I've got one on my desk. So, yeah, that's good.
Well, watch out for those little coupling capacitors. I think that's a risky design in mechanics. And I've seen it twice now. I've seen it twice in the radio astronomy supplies products. I've had it fail in another module that we were working on, and the same scenario. So it's just something that if we design things like that in the future, be wary of that connection with a mechanical socket next to the circuit board.
Great. Also, a request. Would you like to put those in the next Sarah Journal, those two articles?
You're quite welcome to use that. Yep, I'm very pleased to have that circulate. There's some useful stuff in there, particularly that noise measurement technique. If no one was aware of that, it's a great little trick and it works quite well.
That's great stuff. Yeah, any questions for Steve? All right, great job. That's the kind of stuff we really like here. So that's good stuff. Let me see who else is online here. Johnny Cox. No. Richard Flagg.
Just here listening to everybody. So nothing much to add, unfortunately, today.
All right, no problem. Joe?
Excuse me, apologies. No, nothing much to add. I'm afraid I have been engaged in other pursuits, unfortunately, so I haven't had time to do anything. I haven't done for the last couple of months. So, but hopefully now things start changing. I'll be able to get back into it again. And Steve's doing all the work anyhow. So,
I have one more thing to talk about, Rich. There's a bit more progress on our big dish.
Well, go for it.
All right, I won't hold up this one too long. I don't have a lot of photographs to explain the whole story, but this was that worn out jack screw worm gear. So that's the whole assembly as it's pulled apart. It's got two bearings at each end, and the internal thread where the jack screw goes through, that was the bit that wore out. So a pity I don't have photographs to show. What we've done was we've modified this whole worm gear. We've milled out the old worm thread because that was all worn out anyway. So that's been slightly enlarged as an internal sleeve. And then completely new inserts have been fabricated that go inside this. And they're fitted using what's called a Scotch key. So there's a number of Unbraco hexagon screws that go through around the rim, multiple ones that lock the insert into the rest of the body of the worm gear. And we've actually extended now the length of thread that was in contact with the jack screw shaft. So there's a little bit more material to wear out over time. So hopefully it doesn't wear out. We've also purchased and obtained the bellows, the dust protection bellows that are going to go over the whole length of the jack screw to protect the thread from weather. So we've got all the bits. It's now a case of trying to put it mechanically back together and putting it all back up on the tower. And I'm hoping certainly before Christmas, Rich, we'll be having our neutral hydrogen receiver back online.
Oh, great. And Ted will love that data. You get that. All right. Any questions for Steve? And Joe, are you ever going to get out of that dungeon there that you got in your background? Is that a real place?
No, no, it's not. It's
Just checking. I don't know.
I
I don't
just
know
like
about
the
you
look.
guys down there.
I like the look of it. That was all.
That's his garage. It's infinite.
Yeah. Well, when you say down under, I'm thinking Joe's garage there. So. All right. Let's see. Let me see the list here. Mitch.
How are you? Steve has filled in all the details of what we've been doing recently. I did some work on the lead screw, and it's the little problems we're encountering along the way. I'm not sure if they're due to our mechanical inexperience or if it's part of the equipment we got, but we're struggling through it. We're getting there, but the progress is kind of slow. And we'll hope to have something happening by Christmas. So that'll be really nice. A nice Christmas present. We'll keep going till then.
Great.
That's from us, really.
Yeah, the dish or 60-foot dish, they had the same issues when they first started that, and it takes a long time to get that figured out. But once you do, you got a cadre of people that know how to fix it and maintain it. So then you go on to the next big problem. So it's just yeah, never ending but fun. Thanks, Mitch. Hey, I got this iPhone. Who is that on the iPhone that? And do you want to say something? Okay. Alex.
That's me, Rich. I'm sorry. I couldn't get the speaker and the stuff working here. This is Bob.
Okay, Bob.
I'm sitting in downtown Dallas waiting on my brother. We're going to go to a Texas A&M football game. But I thought I'd listen in for as long as I could here and just enjoying the talk.
Okay. Thanks, Bob. And, those Aggies, when I was at University of New Mexico, they'd have to wear boots and swords. And we were in a rifle drill team. And so they're pretty hardcore guys. So
yeah.
fun.
All right.
All right. Okay. Alex, you gave a Drake's Lounge. If you guys haven't seen that, Alex gave a pretty good talk, and it's actually on YouTube now. I asked him if he could just do a couple of minutes to sort of go over what he did there for you guys. So go ahead, Alex.
Okay, I can do that. And I actually have a couple more slides of some data that I processed that I want to show. But let's see if we can go through this. Wait, what's this thing complaining about? Over the months, I have heard comments about LNA temperature sensitivity, and many comments were published about keep them cool. As the night cool, they work better. Ambient temperature changes will change the gain of the amplifiers, but I have never seen it quantified. So it's too hot to do much outside. I thought I would try to characterize this no electric Sawbird since so many people use it. It's optimized for hydrogen, has a nice SAW filter. The bandpass has about 40 dB gain. So let's see. Let me see if I can show you the layout. I only have a few slides from the main presentation, but what I wound up doing was using a small nano VNA. I wasn't sure what the waveform is out of this. I have a 3-stage cavity filter, 1.42 gig cavity filter. So I use that to excite the maybe do it over here to excite the Sawbird, and then I added various attenuators in here. These wound up equaling the effective cold sky and 290K of vegetation. And so I simulated roughly the amplitude of the signal going into the Sawbird of what I was seeing from my radio telescope. the output of it down through a DC block, because this has 5 volts on its connector output for a bias T, and into this nano VNA. This is kind of the setup. The nano VNA, everything was battery powered, so I could run 4 or 5 hours off of this thing without it dying. There's the cavity filter. Here are the attenuators. This is one condition where it was in the refrigerator. This actually didn't work out too well, but back around into the analyzer. And what I measured was something like this. So this was the excitation. It was already band limited. That's all I really wanted. I didn't know what side bands might be created. I don't think this thing actually generates nice sine waves. So this helped to eliminate any kind of out of band response to this LNA. So out of the nano VNA into the Sawbird and back. And I actually measured 4 different temperature conditions, and I acquired a lot of data. Let's see. We'll get down next. I also ran a linearity check. Using the whole setup of the Sawbird into the nano VNA, I imposed a series of physical attenuators, and I wanted to make sure that the range that I was going to be using was within the linear range of this system. And so I was working around in this range, and so it was within the linear range of the whole system. I did a lot of tests. This turned out to be much more of a challenge than I thought. Well, because I really had no idea what to even expect as far as the sensitivity of this device. So there are a lot of false starts. You can listen to it on the YouTube video, but at the end I finally figured out how to do it, and this is a summary of the results. At ambient temperature, I made a small little oven, if you will, or heater to get up to 50 C. This is the refrigerator and this is the freezer. And I did this at 2 different levels, this simulating like 290K and this simulating cold sky. And I was pretty amazed at the consistency, and it doesn't change a whole lot. And if you look here at ambient temperature, around 25 C, it shows that it has a gain of around, whoops, I already lost it, 41.05, and I think it's rated at 42 dB, so that's pretty close to what the Sawbird is spec'd for. But I didn't have anything to compare this to. Bob Strickland sent me this info. He had taken apart one of the Sawbirds and identified the LNA as a 9037. And a little bit of research identified this Corvo as a 9037, and it has the right specs. It covers the right frequency range. It has a noise factor in itself of 0.4 dB and about 20 dB gain. So it uses 2 stages of these. So it's 40 dB. This is the information. There are a lot of data sheets on this, but there's one data sheet that looks like this. Well, without all the dotted lines. And there's information in here that's not obvious. This right from here, you can actually measure the gain versus temperature from this. If you identify the 420 megahertz, expand up that little dotted line, you come up with this. If you interpolate between these 2 numbers, these 2 values of gains at minus 40 and 85, 125 degrees C span, this comes up with minus 1.1 dB variation. That's 0.008. So that falls right in the value that I obtained, if I have the next one, from the experimental data. So I was amazed that I got such consistent results. And so if you convert that over to a 10 or 20 degree C change, it comes up with a variation of maybe a 2-3% variation in power, roughly 0.1 or 0.2 dB variation in gain. And so the question is, how bad is it? Well, maybe not too bad. For a larger scale system where you're doing very high resolution work, a couple % change in gain may be significant. but for beginners, I'd say that's of no consequence. And it's linear, so instead of, you could accommodate for that by putting a thermocouple on the LNA and recording it and doing a mathematical compensation for it. I think that's the end of the story. Are there any questions on this?
That's excellent work, Alex. It's sort of consistent with what I've found too. Remember my earlier report on the Spectracyber low noise amplifier? I found it was a negative coefficient as well. So the gain increases with lower temperature.
But what
And
was
I
that
was getting,
coefficient? Do you remember?
well, I measured minus 0.036 dB per degree C. That was the slope.
Wow.
So it's a lot, slightly higher than that
Wow.
commercial unit. Yeah.
0.03?
0.036 dB per degree C. Yeah, a lot higher than that commercial unit.
Yes.
Yeah.
Yes.
So that's an interesting comparison. Yeah.
So,
The other thing I was going to mention, you've got a nano VNA as well. I have one. And I've used this at lower frequency and put it into an oscilloscope. And you're quite right. It's a square wave coming out.
and
So
I didn't
good
know
thing you
how
use-
I didn't know how that would affect the LNA. So I forced it just to have an excitation over the bandwidth that I was interested in.
through the cavity filter. That was a great idea. Yeah, very good.
The nanos are using harmonics as the LO, so they are definitely square waves, and
Yep.
it'll be the third harmonic, I think, at 1400. So it's quite a good idea to have that filter in there if you're going to depend on it being a sine wave.
And I mean, I'm measuring to hundredths of a dB on these various steps, and it would wander a few hundredths, and I have to sort of average it out over 30 seconds. I went from ambient to refrigerator to freezer to ambient to hot to ambient. So it was 6 steps. It took 3 hours for a temperature cycle. So from setup to teardown, it was about 4 hours. So I spent a good 24, 30 hours doing this test. Like I said, there were some false starts, cable kinks, loose connectors. I didn't know what to expect. So you run a test, you look at the data and figure out maybe what you did wrong.
Need a can of freezer.
A what?
That's a bit hard to control. The only problem is that's hard to control the absolute temperature, isn't it, Alex?
Oh, very definitely.
Yeah.
Well, yes. Well, I mean, I took what I got, but the temperatures were reasonably well spaced. So,
what's the noise figure of that sort of commercial amplifier?
I think it's supposed to be point. I think the specs are 0.8.
Okay.
Let's see. Yeah, 0.8 dB.
Not as good as the Spectracyber.
No, but having a spectrum has some advantages also.
Very true.
Any more questions on this?
Can you put that in the chat window, that report, Alex? I'd love to have a copy. It's good work.
It's on the video. Go look it up on the Sarah videos. There's more detail than what I just showed now. There's probably at least twice as many slides.
Yeah, put that. That's the YouTube on the chat.
I got a copy of that. Thanks a lot.
What I do want to show you, let's see, I don't know if we can. What I do want to show you is some results that I got from processing some data from, I took earlier this year. Yeah, you were sharing. Can you see this?
Yes.
Okay. All right. So in the spring, I took several 24-hour sweeps at different declinations. And this is some software that I wrote. And this is the equivalent hydrogen spectra at these various declinations over a period of 24 hours. And if you zoom in on that, there's a lot of detail. It's pretty interesting. And so I was pleased that I could get this quality of data from basically a 1 meter dish. And this is at 40 degrees declination. This is at 20 degrees. So I'm very pleased that of the configuration, the modification of the scope in a box system to get data that looks like that. Those are 5-minute steps. And so I basically can resolve to, well, certainly a degree, because I could do a little bit better than that, but the system works pretty well. That's the story.
All right. Now there's Alex, put that those Doppler, one of those Doppler charts up again. And there's a I saw this at the VLA. There's a nice chart that has Doppler. Is it Doppler or just frequency change? No, the one before that with the color.
Yeah, I'm trying to get this thing.
Okay. But if that's across the Milky Way, it actually shows that you can determine where the arms of the Milky Way are and things like that based on the Doppler shift, what's coming toward you and what's going away from you.
Yeah.
And so once you get the chart like this, then the question is, well, what part is the an arm of the Milky Way, which is spiraling toward it or away from it. So there's all sorts of science you can get out of these charts. Especially at that detail, I think that you might be able to pick out some structures or some hydrogen clouds or something like that with this.
So right here, this is close to 0, and these are negative. So these are red shifts. So this is moving away. These are positive red shifts. So this is moving away. These are negative. So this area is moving towards us. But I was extremely impressed with the quality of data that I can get out of this system.
Now, is your software is that on MATLAB, and is that available to share?
It's a disaster. I mean, each time I try to go in to try to improve it and get it a little bit more organized, I find something that I need to add. I mean, it may be a year from now, but it's probably a half a dozen programs, and it is not well. You have to edit lines. I mean, this is no GUI. It's not even close to doing that, and it would take me longer to explain to someone how to use it. It'd be better you send me some data and I'll process it for you. I mean, I mean the techniques, the processes are on the video I did July a year ago for the summer SARA meeting. And I'd be happy to explain to anyone the routines, but as far as it's not at that point yet.
Is it comparable to Ezra or for the programs?
I don't know what Ted doesn't really specify what he does with his processing. I don't know.
Okay. All right.
So,
all right. Any questions for Alex? All right, great. Really good stuff. Yeah, check his video out. Let's see. Don Latham.
I'm actually here. Here I am. I should be driving the antenna pretty soon. Another week, and I'll be finding out why it's so weak. And then I'm thinking of a front end using a no-elect and another filter to get simultaneously 1420 and 1.6 gigahertz OH. So I think they're close enough together, and I'll take Pluto, ADALM Pluto that I have that has 2 receivers, and hook one receiver at 1420 and one receiver at 1.64, I guess it is 1.6 something, and try to process them both at once. I think I have a computer that'll do it. And that's my grand plan. See you next spring.
Since you sort of jumped ahead, explain your antenna again, because for people that don't know what you were talking about.
Oh, I have a 16-foot parabola f3.7, and it's mounted on an old scavenged mount that was one of the original Tyros weather satellite mounts from the Pacific Ocean. And it's kind of clunky, but I think I can hold it to about half a degree, which is good enough, I think.
All right. Any questions for Don? All right. Helen.
Hi, I'm just in listen mode today. I've been fighting the flu, so that's all I have.
Okay, thanks.
Thank you.
Well, Monroe.
So the black dwarf candidate that I talked about last month is still okay for October for folks in lower latitudes. For me, I recalculated it, and it turns out it's probably going to be more like mid to late December for my best viewing. But as I stated, I don't have any specific frequencies to observe it at because it's a new candidate, so it has to be characterized. But just something to keep in mind if you've got receiving equipment and a good opportunity to look at it, then you can look at it. The actual get its designation here. I'll put the designation in the chat window.
All right, you got a pretty accurate right ascension declination for everybody to look at.
I would suggest use your Planisphere software, or you can go look up the higher accuracy ARIAN deck from Simbad, and I can put the link to that catalog entry in Simbad in the chat window.
Okay, and I mean, just give a quick overview of what we're trying to find here.
Sure.
And what
you can think of a white dwarf star as the ultimate fate of our sun, because it's not big enough to become a neutron star or a black hole. And what they found is that the progression of a white dwarf, because its energy is going to be consumed over time, and it doesn't do fusion anymore, so it's going to get cooler. And they sort of connected the dots and went out way far into the future, many billions of years, and said eventually we won't be able to see these white dwarfs visually. We still be able to see them in infrared, but at some point even farther out, we won't be able to detect them except in radio, because they won't be visual anymore. They'll descend down to radio, and it's not because they're moving away faster, it's that they're getting cooler. And the ultimate fate is this candidate, which they've identified as it's listed as WD, which is a white dwarf candidate, but it's a very, very old white dwarf candidate. And the idea is to characterize it in radio emissions, which aren't very typical for a white dwarf. So most people aren't looking at them if they're into radio astronomy. But by this thing, being a black dwarf candidate as transitioning to radio, see if this is a white dwarf that is actually already emitting at some frequency of radio. And I would say it's higher frequency because that's usually how higher energy goes to lower energy, as you start at higher frequency and descend to lower frequency. But the other thing that's interesting about this particular white dwarf candidate is it's headed our direction, but not anytime soon. It's just, if you look at the angular motion of it, it's not moving away from us, it's moving towards us. So that's why it's interesting. Okay.
All right, great. Okay, thank you. Let's see, last but not least, Preston.
Hello, Rich and everyone. Well, my excuse this week is I had cataract surgery. So haven't done anything.
Well, that's why you're a radio astronomer, not an optical astronomer, I see.
Yeah.
All right. Get well, and thanks. Okay.
Thank you.
Anybody I miss? All right. That's any other questions? That's all we got. All right. Talk to you guys next month. Bye. Thanks everybody.
Bye.
Many thanks, Rich.
See ya. Bye.
Bye. See you next time.
Bye-bye, everyone. Thank you.